So today I want to talk about, I want to do our first data talk, and it's for the first quarter of A World from Dust and the first two chapters of Atkins, and it's basically taking those and putting them together. And there's one question that actually can connect to both of those, and it's a fundamental question. We say that the universe expanded and that it cooled when it expanded. You can actually use pChem to explain why that happened. I mean, why should it happen in that direction? Why should it not happen in another direction? Well, the answer is in physics, but it's in the branch of physics that's close to physical chemistry, and you can explain it with the equations that you've just used. And if you want to use a word to explain it, you know, we're talking about it after chapter 2. We just talked about entropy. So if you want to use a single word to answer that question, you could do a lot worse than to answer entropy is the reason why the universe cooled as it expanded. But how do you apply our pChem equations to the universe? Well, we've got a little bit of talking to do before we get to that. Really, we're going to talk about all three laws of thermodynamics, because if you think about it, chapter 1 was about heats of reaction, and that was related to the first law. You had chemical bonds being converted to Q. You had a stability, a change in delta H, that would be the heat at constant pressure, right? So you're turning kilojoules per mole into joules. That is a first law thing because it's a conversion of energy. The second chapter, we talked about entropy. We sort of defined entropy with the second law, and we set a lower limit for it with the third law to say it's a number. So we're going to form bridges between these laws and our two books, which actually talk about all three laws. It's just that it's not explicit. I didn't want to have a prerequisite for reading the A World from Dust book to be that you had to have pChem, that you had to understand what these things were. So I tried to explain things as you go, and there's sort of things hidden in it. One of the things that's talked about in chapter 3 is the periodic table itself, and it's how it's built on math. We've been able to talk a little bit about that, but if it's really built on math, we should be able to calculate it, right? We should be able to somehow to calculate the periodic table. Now, you could do that through the quantum mechanics lecture, but like I said, that gets really complicated once you get past hydrogen. So it's not really practical to do that. But there's another way to do math that actually will give you a periodic table. And it starts with the properties, the basic properties of the elements. So over time, you have the universe. We have this chart, or a version of this chart, in the book itself, that we had all hydrogen at the beginning, because we just had protons and electrons. But then stars were able to fuse the protons into more protons together, which made the larger elements. And this is why, over time, you have to build up everything large. You have to build up from hydrogen and helium and a little bit of lithium, maybe. That is why you don't have much of the atomic number 60 in the universe. There just hasn't been time to build up enough of it. And it's really interesting because doesn't this look a little bit like an e to the x kind of graph? This looks like a pretty simple graph, but this is a graph of everything in the universe. And it's organized by atomic number on the x-axis and relative abundance on the y-axis. And you see that hydrogen is still the most abundant thing in the universe. Everything else is sort of following up second place. And so this is physics, why these things work and why you have a dip right here. If you look here, there's a huge dip at lithium, beryllium, boron, and things like that. Those are actually physical explanations that we can give for that. And there's patterns that you can see because the simple physics will result in some simple patterns. One pattern that you can notice right here is notice that there's two lines, odd atomic numbers and even atomic numbers. And so in general, what do you have more of? If you have an atom in the universe and you have atoms right next to each other, so they've had about enough time to collide and come together, what do you have more of? Which one's more stable? An atom with an odd atomic number on average or an atom with an even atomic number? Yeah. But we can't deal with that as chemists because that's physical equations involving the strong nuclear force and all sorts of fun stuff like that. So you've got the even atomic numbers are more stable, and you can talk about why. That goes back to the forces, but those are physical forces, not chemistry. So the changing from element to element is not something that we can do as chemists. It's something that early chemists wanted to do. You know, they wanted to change lead into gold. But it's really physics that can do that. You can slam it together, but it's not worth it. You can make gold out of lead, but it's not worth it. But the cool thing is that as chemists, we can take this graph as basically these elements are frozen in place on chemical timescales and chemical energies, and we can say the more of something you have in the universe, the more of it you will have in your own body. If you take your own body as the system and say, okay, how much of each element do I have in this body? And you do roughly the same graph. This is not nearly as precise as the other graph, but it's pretty similar in that you have oxygen and carbon and hydrogen are the elements that you use the most of. And they're also the elements that are most abundant in the universe. They're actually the 4 top abundant elements in the universe. You have all of them except for helium. So abundance does affect what's in your body, and what's in your body is a reflection of this decreasing trend. You don't have much uranium in your body. Because it has such a large atomic number, there's not much of it around on Earth. And yet, if you look at this, there are also deviations from this pattern that go, and so why do you have more oxygen in your body than hydrogen? You can look at the deviations as well and come up with the chemical reasons for why you need oxygen. Why do you have less silicon than carbon? Well, because you use the carbon. And there's a chemical reason for that. So the universal abundances are actually reflected in biological abundances. Physics and biology are correlated here. So if you look at hydrogen up there, you have hydrogen the most in the universe, and most of those elements that I just circled right there are going to be the elements that are used most in the human body. In fact, you'll see that they're pretty much all, you need them in the kilogram to gram range to live. You need to eat those atoms. And so, for instance, you can look at things. You see titanium right there. Titanium is less abundant in the universe. Is that part of the reason why titanium doesn't show up over here? Other reasons as well, to be sure, but something that's really not abundant, like boron and beryllium and lithium, you don't really use it biologically either. So what's outside ends up inside. Another, it might be the reason why we don't use aluminum. There's other reasons as well, but we start with abundance. And we don't use silicon because carbon's a better option, and carbon is more abundant. Okay. Then there's questions like, why don't we use that much nickel anymore? Those will be covered in later chapters.